So our next speaker is going to be Jeff Green, and he'll be talking about the Driftless area also. But first, we're going to watch some videos that he had a part in making, I believe. Can you all hear that?
Yes.
Great, thank you.
In southeast Minnesota, we are fortunate to have an abundant supply of groundwater. It is the water we drink and the source of water for area trout streams. But where does groundwater come from? How does it move? Nature has created a complex underground system that collects and stores our groundwater. All groundwater was once rain or snow. Rain and melted snow soaks into the ground, moves through the soil and the rock beneath our feet, and eventually, over days, weeks, or years, may flow naturally to a spring or stream, or be pumped from a well for drinking water. The water we drink is not stored in underground lakes. It is contained in and moves through cracks and connected spaces within sediment and rock. These layers of sediment and rock that hold groundwater are called aquifers. Groundwater contained within aquifers can move downward due to gravity, sideways due to different rock properties, and upwards due to pressure. Predicting where groundwater will go is not easy because the various layers of sediment and rock influence the water's path. We'll use Minnesota's Root River watershed to explain how groundwater moves across 3 different landscapes in southeast Minnesota. From west to east, these landscapes include Glacial Till, Karst, and Bluffland Karst. Let's first discuss the Glacial Till landscape. This area is located at the headwaters of the Root River watershed in eastern Mower County. In this landscape, up to 200 feet of glacial sediment covers the underlying bedrock aquifers. The glacial sediment consists mostly of till, which is a dense and compacted mixture of clay to boulder-sized material laid down directly from glacial ice. The thickness and amount of clay found within this glacial till landscape affects how rapidly groundwater moves. Most of the glacial sediments in this area are dense and clay-rich. This clay sediment slows and restricts some of the downward movement of groundwater to underlying aquifers. In isolated areas, buried sand and gravel channels left by glacial streams are located in layers of till. These may serve as shallow aquifers and allow for faster water movement. Most rain or snowmelt that hasn't evaporated or been used by crops soaks into the top 4 to 5 feet of soil and then flows through a network of underground drainage tile. Water directed through tile and drainage ditches moves quickly to streams. Despite the thick glacial till and artificial drainage, a small amount of precipitation slowly soaks downward past the drainage tile and into the aquifers that lie below. The Karst landscape in Fillmore County is the central landscape of the Root River watershed and is our second area to explore. Here, the bedrock is largely made up of carbonate bedrock, or more commonly called limestone. Only a few of the glaciers from long ago advanced into this area. Since the end of glaciation, most of the glacial sediments have been eroded away and have been covered by a thin layer of topsoil that contains less clay. This soil, in many places less than 10 feet thick, allows water to quickly soak into the underlying bedrock. All rocks break down naturally over time, but what is unique about limestone bedrock is that it erodes relatively fast. This accelerated erosion is caused by a chemical reaction in which slightly acidic water in rain and soil dissolves the rock. Limestone dissolves at a rate of about 1/2 inch every 1,000 years, a rate similar to those apparent on marble gravestones, where inscriptions from the late 1800s are becoming unreadable. Although we may think this rate is slow, it is quite fast from a geologic perspective. Since the last glacial period, This would equate to about 5 inches of weathering on a rock face, or close to a foot of weathering on opposing walls of a fracture. The resulting dissolved bedrock is known as karst. Karst is characterized by springs, sinkholes, disappearing streams, enlarged bedrock fractures, rapid groundwater flow, and caves. In karst landscapes, the distinction between groundwater and surface water is oftentimes not clear. For instance, groundwater may emerge as a spring, flow a short distance above ground, and then disappear back underground. This same water could then re-emerge farther downstream again as surface water. While sinkholes are a dramatic feature in karst, most rain and snowmelt becomes groundwater not by flowing into sinkholes, but through infiltration into the ground and rock throughout the entire land surface. Over time, karst bedrock develops a variety of cracks and spaces that water can enter and move through at different speeds. There are 3 primary types of spaces in karst bedrock: conduits, fractures, and pore spaces. The size of these spaces dictates how fast groundwater can move. Conduits are similar to underground pipes that move water rapidly. In southeast Minnesota, conduits large enough to walk through are found at Mystery Cave, Niagara Cave, and many other cave systems. Groundwater traveling through conduit networks can move extremely fast at a rate of several miles per day. Fractures are slightly smaller. Groundwater traveling through fractures moves at a moderate speed and can travel at rates of dozens to hundreds of feet per day. The slowest groundwater movement occurs in tiny pore spaces contained within the rock itself. Here, groundwater in pore spaces may take several years to travel a few feet, or it may not move at all for long periods of time. Limestone rock dominates most of the upper bedrock layers across southeast Minnesota. However, layers of sandstone and shale are also present. Shale is composed of compacted layers of mud or clay that are less permeable and soluble than limestone. The presence and thickness of shale layers within the bedrock affects the speed and direction of groundwater movement. Compacted shale layers act like a barrier, slowing but not completely stopping the downward movement of water. The presence of shale redirects groundwater to move sideways, where it can emerge as a spring. The source of groundwater and its flow path can be local or regional. Local groundwater is typically found at shallow depths above shale layers. This water has only traveled a short distance and may only be days to decades old. In contrast, regional groundwater is found deeper and below layers of shale. It may have soaked into the land surface from far away and may be decades to centuries old. Depending on location, groundwater discharging from a spring or pumped from a well is often sourced from a mixture of both local and regional groundwater. The deep valleys and bluffs near the Mississippi River in Houston County, called Bluffland Karst, is our last landscape to discuss in the Root River watershed. Long ago, melted water from glacial ice that covered the Till landscape and other areas of the state flowed east, eroding older glacial sediments, and carved small valleys as it traveled across the karst landscape. As this powerful water flowed further east to the Mississippi River, it carved deeper and much larger valleys and bluffs into the softer sandstone and uppermost shale bedrock layers. In the bluffland landscape, precipitation falling or melting in the upland areas moves quickly into the shallow karst and sandstone bedrock aquifers. Along its flow path, the water encounters shale layers that cause groundwater to move sideways, where it flows to springs and streams. In some locations, these streams can disappear underground and then reappear downstream, or in a completely different valley. Bluffland streams cut deeper through the various layers of rock, including shale, as they flow east towards the Mississippi River. Older groundwater that is stored in deeper bedrock layers below the shale is under pressure. This pressure causes groundwater to flow upwards and towards the valleys. Due to this upward flow, streams and springs in this area receive a greater proportion of much older regional groundwater. Groundwater pushing upwards from deep aquifers provides a consistent supply of water that is distinctive to this area's cold water trout streams. This scenic landscape and the life it supports is closely tied to the fascinating and complex pathway water takes through it. By understanding how groundwater moves differently within the glacial till, karst, and bluffland karst landscapes, we can understand how groundwater moves throughout much of southeast Minnesota and the Driftless region. The next time you drive through the area, look at the rock exposed on the sides of the road and consider how this region's geology affects the movement of water, both on the surface and underground. Understanding how groundwater moves in southeast Minnesota is key to understanding how contaminants can enter groundwater. Most contaminants found in the region's streams, rivers, and drinking water are a result of human activity on the land surface. Some commonly detected contaminants include bacteria, pesticides, fertilizers, and chloride. These contaminants can enter aquifers, where they might move at many different speeds and across great distances. One of the most mobile contaminants found in Minnesota groundwater is a form of nitrogen called nitrate. Although nitrate is an essential nutrient, excess sources primarily come from fertilizer, animal manure, and human waste. In southeast Minnesota, where the landscape is less populated, nitrate largely comes from cultivated cropland. Let's examine how nitrate can move into drinking water and surface water across 3 unique landscapes in southeast Minnesota. In the glacial till landscape, karst aquifers are present below the glacial sediments, but nitrate is less likely to reach these aquifers. This is because the thick layer of clay-rich glacial till acts like a barrier and provides some protection to deeply buried aquifers below. Additionally, most water soaking into the ground is captured by a network of drainage tile that flows directly to surface water ditches and streams. Although these factors create less risk to drinking water here, nitrate moves downstream in creeks and rivers to the karst and bluffland landscapes, where it can move quickly into the bedrock and mix with groundwater. In karst, nitrate can travel to both surface water and drinking water by moving rapidly through shallow soils and into the underlying fractured bedrock. Unlike the till landscape, dense layers of clay are no longer present. This means that the soil's ability to naturally filter potential contaminants is reduced. Leaching, or downward movement of nitrate through the soil, is the primary way nitrate is lost to groundwater. Leaching occurs on all cropland acres throughout the region. Since nitrate dissolves in water, it follows the same path groundwater takes through the bedrock and can eventually end up in a drinking water well, spring, stream, or river. Although sinkholes are an important and visible feature in karst, they are a minor pathway for nitrate to enter groundwater. However, after a snowmelt or a heavy rain event, overland runoff into sinkholes can provide a direct connection for contaminants to enter groundwater and surface water. The movement of groundwater to drinking water wells in karst can be difficult to predict, but in general, layers of shale can help slow nitrate from reaching older, deeper groundwater. Results from drinking water monitoring in this landscape have shown that higher nitrate concentrations are usually highest in groundwater that's closer to the surface, while lower concentrations are found in deeper wells that pump groundwater from below protective shale layers. Although well depth is a key factor affecting nitrate risk to drinking water, well construction and maintenance is also important. Wells not properly maintained or constructed using modern well drilling techniques are more vulnerable to contamination. For instance, Over time, well casing may corrode or crack, allowing water to enter the well near the land surface before contaminants can be filtered out by the soil. Casing also plays an important role in determining which area of the aquifer a well draws water from. When comparing two wells at the same depth, the well with shorter casing may have much different water quality, even though they are right next to each other. Similarly, grouting is intended to fill any gaps between the casing and surrounding bedrock. A poorly grouted well may allow water from the land surface to run down the sides of the well casing and directly into the well. This can help explain why a deeper, poorly constructed well might have higher nitrate compared to a shallower, properly constructed well. In the Bluffland Karst landscape, the upward flow of older and deeper regional groundwater affects the concentrations of nitrate. Older groundwater that can be several centuries old mixes with younger water that has higher nitrate. This mixing process reduces and dilutes nitrate in bluffland streams and some aquifers. As it relates to drinking water, shallow wells are just as susceptible to nitrate contamination in the bluffland setting as in the karst landscape. Despite nitrate dilution from mixing of older groundwater, nitrate can still move to deeper aquifers, slowly increasing in concentration over time. Long-term water monitoring has shown that nitrate concentrations are increasing in groundwater flowing to bluffland streams. This rate of increase is about 3% per year. This does not necessarily mean that nitrogen sources from the land surface are increasing at this same rate, just that nitrate leached today, or yesterday, or 40 years ago, have not fully made their way into deeper groundwater. This delayed response, called lag time, is also occurring in some deeper drinking water wells, where nitrate concentrations are slowly increasing at a similar rate. Over the past several decades, communities in southeast Minnesota have taken important steps to protect groundwater. Many farmers are using more efficient management practices on cropland. Rural homeowners are sealing abandoned wells, fixing leaky septic systems, and landowners are keeping sinkholes free of trash. Despite these efforts, ensuring clean water for future generations will be an ongoing challenge, and additional efforts and focus will be needed to reach our clean water goals and standards. The next time you drive through the area, consider how easily actions at the land surface can impact groundwater. Then continue to think about what you can do to protect this vital resource for everyone to enjoy. This flat agricultural area in eastern Mower County is called the Glacial Till Landscape. This is where the Root River begins its 80-mile course to the Mississippi River. Network of subsurface pipes called drainage tile are placed 4 to 5 feet below the ground so crops can be grown. This tile directs about 20 to 30% of the annual precipitation to drainage ditches and streams. A small amount of precipitation slowly travels to deeper groundwater or runs off the surface, while most is evaporated and used by plants. Till is a dense mixture of clay to boulder-sized material that was laid down directly by glacial ice. Up to 200 feet of till covers the underlying bedrock. The thickness and amount of clay within this till affects the movement of groundwater. This dense blanket of compacted clay acts like a barrier and slows the downward movement of groundwater. In isolated areas, buried sand and gravel channels left by glacial streams are located in layers of till. In these locations, water flows faster into the underlying aquifers, and younger water can mix with older water. Younger water is often from aquifers located above shale layers and can be years to decades old. Older water is typically contained deeper in the glacial till and bedrock layers and can be decades to centuries old. In many cases, drinking water is a mixture of both younger and older water.
Grammarly does more than catch errors. With Grammarly, you can find
The karst landscape is located throughout southeast Minnesota. Over thousands of years, carbonate bedrock, also called limestone, is eroded away by slightly acidic water in rain and soil, creating karst features. Karst features include enlarged fractures, sinkholes, caves, springs, and disappearing streams. A thin layer of topsoil allows water to easily soak into the underlying bedrock. Once in bedrock, water moves quickly to shallow drinking water wells, springs, and streams. Although some rain and melting snow moves from the surface to groundwater through sinkholes, most soaks into the ground across the entire land surface. The distinction between groundwater and surface water is not always clear. Groundwater may emerge as a spring, flow a short distance in a stream, and then disappear. This same water could then re-emerge within hours or days, farther downstream again as surface water. Layers of shale are less permeable than limestone and hinder the downward movement of water. Instead, water travels sideways, following the easiest path across the shale. In areas of the landscape where the shale has been removed by streams or erosion, younger local groundwater from above the shale mixes with older and deeper regionally sourced groundwater. Younger water is often from aquifers located above shale layers and can be just days to decades old. Older water is typically contained deeper in the glacial till and bedrock layers and can be decades to centuries old. In many cases, drinking water is a mixture of both younger and older water.
The rocket equation, it's a beautiful thing. No astronaut
The Bluffland karst landscape is the scenic area where the Root River completes its 80-mile course to the Mississippi River. Long ago, powerful meltwater from distant glaciers carved large valleys and bluffs in the softer sandstone and shale bedrock layers. Groundwater movement in the uppermost bedrock layers and near the fractured valley edges can be very fast. In some locations, streams can disappear underground in the shale and sandstone layers and then reappear downstream or in a completely different valley. Shale layers act as barriers and cause groundwater to move sideways, where it flows to the surface within the valleys. Below the shale layer, deeper sandstone bedrock layers are under pressure. This pressure forces groundwater to move upwards and toward the valleys. Streams and springs in bluffland valleys receive a much greater proportion of older regional groundwater. Some of this water may have infiltrated the land surface from far away and be decades to centuries old. These deeper aquifers provide a consistent supply of water that is distinctive to this area's trout streams. Younger water is often from aquifers located above shale layers and can be just days to decades old. Older water is typically from aquifers below protective shale layers and can be decades to several centuries old. In many cases, drinking water is a mixture of both younger and older water.
Hi, Jeff. You're still sharing your screen. So if you want to just switch to your PowerPoint application, we should be able to see your PowerPoint presentation.
Hey, Meredith, you're still muted.
Can you
Okay,
guys hear, can you hear me?
I thought I had killed the meeting.
I can hear you, Jeff.
You can,
Yeah.
okay, good.
You're on.
I'm on. All right.
Thank you.
All right, good I guess it's afternoon there. It's still morning here, barely. I'm Jeff Green with Minnesota Department of Natural Resources, which I have that title till Tuesday. Tuesday, I am actually retiring from the state of Minnesota. So I was asked to speak about groundwater flow. You just watched all those videos. I hope you enjoyed them. They were a very long process getting those made. Lots and lots and lots of changes and edits and tweaks, but we're pretty proud of them. We've got several different sources of funding that the citizens of Minnesota have voted in, a lottery and an extra sales tax, and those monies help fund things like this. And it's actually funded a lot of information. We have a lot of our Karst information online. So I'm going to talk about groundwater and Karst, and hopefully you can all see that. Meredith, you things look okay, or Dan?
Looks good.
All
Looks
right,
good,
one.
yes.
All right, well, we're going to talk about the driftless area, dying in the driftless. As Dawn talked about, the driftless area is unique, it's beautiful, and it's very fragile. And many of us have been doing a lot of work for a long time trying to understand the groundwater flow dynamics here, because if you don't understand something, it's really hard to manage it. This is a cave spring down in Fillmore County, actually not very far from where Don Ryan is right now. Well, the way water moves through the landscape and how things work is really has its beginning with the hydrologic cycle. We've got rain here in Minnesota, snow, lots of snow falling from the sky, Some of it runs off, some of it soaks in, is used by plants. Some of it makes it down deep enough where all the pore spaces are filled and we have saturated flow, and that's where we get groundwater. And we like to talk about aquifers. And I've talked to a lot of people over the years who think that there's a specific definition of what makes an aquifer. If you look at this definition, it's just a layer of sediment or bedrock that can yield economical quantities of water to wells or springs. And that economical quantities, that's really open to interpretation. Here in Minnesota, southeast Minnesota, we have areas that are kind of the Saudi Arabia of groundwater. Even here in Rochester, Minnesota, we have multiple aquifers yielding 500 to 1,500 gallons per minute of water when you sink a large production well into them. We have places where you get 5 or 10 gallons a minute. We don't consider those aquifers. When I was out in the Nebraska Panhandle, my wife and I were out there for 3 years, and up there, people would drill wells into the pure shale, and if they got 5 gallons a minute, they thrilled. That was their aquifer. We wouldn't even dream of developing that here in southeast Minnesota, but over there, that was their aquifer. When we look at aquifers, we want to know how much water does it hold, how much water can it yield, and how fast can that water be withdrawn? How can we use it? And you start off, you got to look at the number of pores or cracks, the size of those pores or cracks, and how those pores and cracks are connected. This is from the US Geological Survey. We've got sands, where the primary openings are the pore spaces between the grains or fractured rock. And then you get secondary openings that, especially in limestone and dolostone, are caused by karst processes, the dissolving of those soluble rocks. And those are secondary openings, but you really want to characterize all these to understand how water is moving. We have unconfined aquifers where the pressure in the aquifer is the same as the atmospheric pressure. And then you'll have aquifers that are confined. They're being squeezed by the material above, and that makes them artesian, and the water is above the top of the aquifer, an artesian aquifer. People think artesian wells are always flowing. They are not. Some do flow above the land surface. But the definition of an artesian aquifer, artesian well, is that the water level is above the top of the confined aquifer. And water is a unified resource. It doesn't respect boundaries. It follows preferential flow paths. There's a classic groundwater flow characterization talks about aquifers being basically acting like saturated sands all the time, and that's not the case, particularly in bedrock. And actually everywhere water will follow preferential flow paths because it follows the path of least resistance. That's what water does. And really hydraulics drives the system. How much pressure is there? What's the relationship in that aquifer between where the water is going in and where it's coming out? But the hydraulics drive, but the geology steers. And you saw that in Dan Doctor's talk, how the geology has a tremendous impact on how groundwater moves. In Minnesota, you saw something like this from Dan earlier. 500 million years ago, we were at the equator, and southeast Minnesota was covered by water, shallow seas that came in and came out, and they left behind our layers of sand and clay and limey materials that have make our limestone and our shales and our sandstones. Oops. There we go. And that left behind this thick, and we're talking 1,000 feet or more of sediment that lithified and became our aquifers and our aquatards, or our low permeability layers. And what we found down here is the water is following, like I said earlier, these preferential flow paths. This side is the lithologic geologic column for southeast Minnesota. The yellows are coarse sands, fine to coarse sands. The greens are the carbonate rocks, the limestones and dolstones. And the brown are the fine-grained rocks that we consider aquatards. As you can see, even those aquatards, and also in the aquifers, these black lines are preferential flow paths. They're bedding plane fractures that have been enlarged in many cases, and the water follows those. This is a plan view of southeast Minnesota. The pastel colors are all carbonate rocks. As Don mentioned, down here we had the glaciers come in, and southwest Wisconsin was just truly driftless, and a little bit of northeast Illinois. It was not covered in glaciers in the last several million years. Southeast Minnesota was, but it's been probably close to 1 million years. So it's preserved our topography. And here's the driftless area again. And where we have shallow unconsolidated materials above these carbonate rocks, that's where we get our shallow karst or our active karst. As you go west, you still have karsted bedrock, but it's covered under a couple hundred feet of glacial material. And in karst, our groundwater is really focused on going through what we call conduits. And here's one of our conduit rocks. We pull these out of quarries every once in a while. Like there's one of these sitting outside the geology building at the University of Minnesota Geosciences building up in Minneapolis. This is a camera case from the old days. And it gives you an idea of scale. Imagine these things, they're like the size of a garden hose or bigger, and you can get a lot of water flowing through them very rapidly. And that's pretty characteristic of karst. And this is another example. This is called the spigot. It's in, I believe, Spring Valley Caverns here in southern Minnesota. And we call that turbulent conduit flow. A lot of water is basically going through a pipe. And that's what we see in karst. Here's Niagara Cave, which is one of our 2 tour caves. This is not the underground waterfall, but it does have an underground waterfall. That's about 60 feet high. And as water moves through karst, moves through those conduits, it comes to springs, and they're the discharge point for the groundwater system. And they're the place where groundwater and surface water meet. This is one of the springs. If you would come here and go on a karst tour with me, we would go see this. It's called the Fountain Big Spring. The rest of Minnesota has Long Lake. We're the land of 10,000 lakes, courtesy of the last glaciation. And the rest of Minnesota has Long Lake, Mud Lake, Round Lake. Down here in the southeast, in the karstlands, in the driftless area, we have the Big Spring. We have at least 6 big springs. I'm guessing Virginia has more than 6 named big springs, but this is the Fountain Big Spring, called so because the early settlers called it a natural fountain. And it looks pretty nice right now, but this is during spring runoff. And what we see in karst is there's really, and the word I use is there's an intimate connection between the land surface and groundwater. Things you do on the land surface can get into the groundwater in a matter of minutes. That connection makes karst groundwater very vulnerable to pollution. One of the things we've seen, like in this spring, is we will, at least this spring is normally 48 degrees, and when we get significant snowmelt runoff, the spring will drop to 37 degrees overnight. There's that very intimate connection. The other thing you see in karst is the line between surface water and groundwater merges, it blends, because you don't really know. It depends on what instant you're looking at. This water, when it fell from the sky and ran across a landscape, it was surface water. It sank. It's been groundwater for 12 to 24 hours, comes out of the spring. and it flows downstream, it's surface water, then it sinks again, and it becomes groundwater. And at that point, you lose track of it. So if you ask, is it groundwater or surface water? The answer is it depends. At what instant are you looking at it? And I'm sure it's that way in Virginia, and it's that way in karst landscapes. It's that intimate connection. This is just an example of that. This is a high resolution LiDAR topography map just south of Rochester. This is a blind valley. It's a series of sinkholes that have coalesced and ends at a steep wall, and there's an opening at the bottom. We poured dye in there. This is a big spring in a farmyard. And I was very fortunate because the farmer who lives there, turns out he goes to the same church I do. So we get along. And we poured this dye. It was a red dye, rhodamine. And this shows that we poured it on the afternoon of February 15th. One of the things we do in Minnesota is snowmelt dye tracing. We use a snowmelt runoff to get out in the farm fields where we couldn't get a water truck because you need water to push your dye in. We poured the dye, and this is around visible levels of this rhodamine dye. And the spring turned pink. And when I went to go get a sample that next day, the farmer allowed us. He was hoping I would never do that again because his wife and granddaughter were extremely upset. The spring turned pink. Their horses wouldn't drink the water. I don't know if they could taste the dye or see the dye, but the horses wouldn't drink it. And that made his wife and granddaughter pretty unhappy. And he hooked up an old well and got them some water, but he very politely asked me to never do that again. And also want to bring in this concept of regional flow, which was mentioned in the video. We've got thicker sediments, and as you get farther west, you'll also get water going through deeper layers. But you get this older water going along, and then where it's active karst, in this case, this is near Austin, Minnesota, the home of spam. The red arrows are recent water, and what happens is water goes through the thin sediments through the karst and gets into the deeper bedrock units, and that water becomes a blend. And this recent water with high nitrates quite often is diluted by the older water. And it's a complex system. The concept of this regional flow, that's been in the last number of years, has been an important consideration in looking at groundwater. Now I end with this. Back in 2015, it was March 17th, and I was pouring dye into an unnamed stream in southeastern Minnesota in Houston County. And lo and behold, 6 hours later, the Chicago River turned green. The dye went 245 miles in 6 hours, and that's faster than a moped. And I'm done. I'll take questions. If you're a Zippy the Pinhead fan, you recognize Culvert Man. So I am done. Questions? I'm going to stop sharing here if I can figure out how to do that.
Thank you, Jeff.
Yeah, thank you, Jeff. Now, was that my question is, I'm going to just butt in front of everybody. Was that last kind of a joke?
Yes, that was a joke. Dan, doctor, has seen that before. I showed that at we gave a talk when we had the sinkhole conference here back, I believe, in 2015. And I showed that. And if you're in the dye tracing community, that's really good humor. I got lots of people laughing about that because it's dye tracing humor. But yes, that was a joke.
Thank you. I was laughing.
Well, that's good. I'm glad somebody did. I'm sure Dan did. He understood what I was doing. Anyway.
I did too.
Questions, questions from anybody?
Well, Jeff, on that concept, you did mention regional flow, and there may be some people on here who aren't familiar with that idea. That humorous anecdote that you mentioned, the dye going in the ground in Minnesota and coming out in Chicago, of course, that's humor. But regional flow actually can travel many miles. And as you've also noted, you can have dye go in the ground, travel several miles, and come out in a matter of days to weeks. And so I'm curious, in the course of your tracing, what are some of the longer transit times or transit lengths that you've documented for dye moving underground in Minnesota?
Well, the longest trace we did was from another blind valley, and the dye went, it was either 12 miles in 10 days or 10 miles in 12 days. I don't remember, but the water actually left the river basin, which was the focus of those videos, and went to the upper Iowa River right on the Minnesota-Iowa border. We have seen in multiple systems where we pour dye in, and it will take a year to go a mile through some of our carbonate rocks. That same carbonate rock system, however, has other places where we pour dye and it goes over 2 miles in 10 hours. So we've seen that. And then the other thing we're seeing in, we've got some pseudo-karst systems, which are sandstones and shales and dolostones that act like karst when it comes to water flow, but they don't have caves and sinkholes and things like that. So we call them pseudo-karst. There we will see dye, the leading edge of dye go through 500 to 1,500 feet per day to a spring from a disappearing stream. But then, and it'll be like mile, 2 miles to the spring, but then 2 years later, we're still detecting our dye. So that's pretty sobering. It's telling you that what we do really has an impact in later years. So does that answer your question, Dan?
Yes, it does. Thank you. Yeah, we're definitely talking miles and miles, but probably not the hundreds of miles that it would take to go from Minnesota to Chicago.
Yeah, I don't know as there are karst systems like that, but there certainly could be. Kelvin Alexander, who was Dan's professor when he did his master's and PhD at the University of Minnesota, and I've worked with Kelvin for a long time now, and has been my mentor and friend, and he has a comment that the threshold of surprise in karst should be very low. And I think that's kind of the modus operandi. You really have to be mentally flexible to think about karst systems because there are always surprises.
Hey,
Other
Jeff.
questions? Yes.
Jeff, there's at least 2 in the chat. I believe it's Danny asked, how did you find out about the results of your dye study?
How do we find out? Well, what we do, we either take water samples or we use little packets of coconut charcoal we call bugs. And as the water from a spring flows through that bug, if it has dye on it, the dye gets stuck on the coconut charcoal, and then we pull that bug and take it to the University of Minnesota lab, in the case here. And they use a scanning spectral fluorophotometer to analyze the water. You strip anything off the bugs with a strong basic, I believe it's a basic solution. And you then analyze that liquid and look for the dye. So that's how we look for our dye. We try not to have the dye be visible. For some reason, people get pretty upset when they see colored water flowing out of a spring. It's become kind of standard down here. If someone observes colored water, our pollution control agency or our Department of Health will call me and ask me if I've been dye tracing. So like I said, we try to stay below visible levels. And that's, so we do the sampling to find our dye. And it works quite well. We have pretty high success rates finding our dye.
Okay, Danny, I hope that answered your question. Sharon Rittenauer's son had to go to dance class, but he wanted to know if other contaminants, just making sure I'm not.
Yep, I'm reading the chat.
Okay, travel in water the same way nitrates do, like microplastics.
I wouldn't think microplastics would move. I mean, like nitrates. I mean, nitrates are ions in the water molecules. So I wouldn't think they would, but like microplastics, I mean, I know microplastics are all over the place. I would not be, I mean, I would be surprised if our springs that are connected to the surface didn't have microplastics. I would assume they would. So I mean, they can travel. One of the things that's been used for dye tracing is people would use lycopodium spores, which are club moss spores, and they would stain them with dye and then pour those and look for them in springs. So I would think microplastics can move quite far. Dan Doctor, what do you think? You work for the USGS. You guys got it. You guys know everything.
I wouldn't doubt it. I think we could find microplastics in all kinds of water, especially in karst. You alluded to the filtration capacity in our discussion earlier, Jeff, about sand. And when you have a lot of sand between the recharge zone and the aquifer, it can act as a filter. But that's not the case in many karst areas. So, and I know they've been able to identify microplastics in precipitation on the tops of mountains. So I do not doubt that it's in the water.
Yeah, and one of the things I've been working on, one of the things I kind of hate to leave when I retire, hopefully I can stay involved. We've been working with our Department of Health here because they are finding things like cryptosporidium and giardia, you know, big, relatively big microorganisms in wells that have 50 feet of dry sand above the water table, and yet they're finding these microorganisms in their water supply. And we've been dye tracing and trying to help them figure out what's going on. Any other questions?
Okay, two more questions that might be about what we have time for because need another break. Ray Keeler asks, what are the responsibilities on cross-jurisdictional contamination? And then I think Ken asks, no, somebody else asks, after a week or two, how do you know that it is your dye?
Well, let's do that second one last.
Okay.
We do put out samplers before we trace, looking for background levels of dye. We use primarily 3 different dyes here. We use a red dye, sulfur-green B, actually it's pink eosine, which is a reddish dye, and then uranine, or also known as fluorescein, which is a green dye, which is actually what ophthalmologists put in your eye when you go for an eye exam. They use it to trace your, your blood vessels in your eyes. So we try pretty hard to look at backgrounds and use dyes that aren't already present. As you get long on a dye trace, long 6 months to a year, you can start wondering if what you're seeing is your dye. The good thing that happens is we'll have lots of samplers out and charcoal packets. So if we start seeing widespread hits with our dye, then we start considering that could be something else. The green dye fluorescein, that is used quite a lot. It's what makes antifreeze green. And so we do have areas where we can't use that dye because we aren't clear if it's our dye or not. So it's based on dye tracing is an art and a science. And as you look at the results, you've got to look at everything in the landscape. So we can be pretty confident because of the quality control we do. And in terms of, and someone said the longest known dye trace is 39.5 miles in 16 days. That's a long dye trace. The other question was about the jurisdictional or cross-jurisdictional contamination. That's a real good question.
I'm missing, this is Ray Keeler, I'm missing the comma. I'm in Arizona, we have some really major large landowners between Forest Service, Park Service, Bureau of Land Management, tribal lands, highway systems crossing all of these, and Arizona Game and Fish, and we have highways that are multiple thousand feet above fish hatcheries, for example, crossing over from, say, Forest Service or Highway Department. How do those responsibilities play out? And here's my catalyst. 2 weeks ago, we had a 3,000-foot survey that went from Forest Service to Indian lands. And multi-section drainage. That's my catalyst of asking this question.
Well, I'm not sure I can answer it. The responsibilities, I think, all depend on, well, federal law and state law. I did take a couple of classes when I was in graduate school in W-Madison. I did take a class in water rights law and land use law. The problem you have is that the pollution, the contaminants and groundwater, of course, don't follow jurisdictional boundaries. And you get things like, the federal government has to agree to be sued. The different agencies, they may or may not care about contamination. I know working for the state of Minnesota, I mean, I got a call a number of years ago from a guy who was telling me where he lived, and there was a limestone quarry. He was worried it was going to affect his well. And he described where he lived, and I was like, well, he lived on the Minnesota-Iowa border. The road in front of his house, if you crossed the road, you were in Iowa, and he was complaining about this limestone quarry in Iowa. And I said, what do you want me to do? We want the Minnesota Department of Natural Resources to do about a quarry in Iowa. And he said, well, water doesn't stop at the state line. And I said, that's very perceptive. You are absolutely right. But our authority does with in the state of Minnesota. So it is a problem. And I don't really think I can answer it because it depends on what state you're in. Minnesota, Wisconsin, where I grew up, we're riparian rights states. Arizona is drawing a blank now. Well, basically, Arizona is first in time, first in right when it comes to water. So
We have a meeting set up on Monday to inform one of the land managers that this underground hydrology is going to happen and get to inform them that something's going on. There's no pollution at this point that we know of, but we're sort of going to add that they have a responsibility to be aware of.
yeah,
And I think preventative is the easiest way.
Hey,
Yeah.